In the previous class, we have studied about occurrence of the clay minerals in soils and methods of their identification. And we also studied about an important parameter called specific surface area, and we said that the specific surface area is inversely proportional to the particle size. If you look into this chart, this graph shows variation of specific surface area AS in meter square per gram or specific surface area with particle size, and on another axis water content is plotted here. For different minerals, 1 quartzite, 2 kaolinite, 3 illite, 4 mantomolite. You can see here, with an increase in specific surface area, there is an increase in water adsorption content. With an decrease in particle size, an increase in specific surface area can be noted. So, different variations of this for different minerals can be seen here. 1 is for quartzite in this range, 2 and 3 for kaolinite and illite, and 4 for mantomolite. So, in addition to this, we also saw clay and water interactions and also defined adsorbed water and cation exchange capacity. We also said that with increase in specific surface area, there will be an increase in the cation exchange capacity. Now, having seen about clay and water interaction, now let us look into the soil structure or soil fabric, which is nothing but arrangement of the soil particles relative to each other. So, in this lecture, we will be seeing about the arrangement of the soil particles, particularly for coarse grained soils and fine grained soils. So, before looking into this arrangement, let us try to look about the particle forces and their behavior. The behavior of individual soil particles and their interaction with other particles is influenced predominantly by two forces. One is the weight of the particle, that is weight force F suffix G, and particle surface forces, that is F suffix S. So, the behavior of individual soil particles and their interaction with other particles is influenced predominantly by two forces. One is weight force and another one is the particle surface forces. Let us see how they relate with each other and influence in particle arrangement. Weight force of the particle is the result of the gravitational forces and is a function of the volume of the particle. For example, for equidimensional particles such as spheres of diameter d, suppose if you represent a particle as a sphere of diameter d, the weight Fg is directly proportional to dq. So, with an increase in particle size, the gravity force increases. If you consider in this slide, a clay particle is shown here. Clay particle is predominantly represented as a platelet shaped particle, and the surface which is shown with negatively charged surface. So, particles are surface forces are often electrical in nature, and they are caused by unsatisfied electrical charges in the particle crystalline structure. That is, there will be always net negative charges on the both sides of the surface of the clay particle. So, surface forces Fs are directly proportional to the surface area, and hence for the equidimensional particles Fs is proportional to the square of the particle size. So, we said that as with a decreasing in particle size, there will be an increase in the specific surface area. That means that the surface forces Fs are directly proportional to the surface area, hence for equidimensional particles Fs is proportional to d square. That means that for particles with finer in size, the surface forces are directly proportional to square of their its size. Now, if you compare the variation of Fg by Fs is proportional to d. So, if you see here, as the particle size diameter increases, the ratio of Fg by Fs increases. Thus, for the larger particle sizes, which include soil particles in the coarser fraction, that is greater than 75 micron or 0.0075 mm or 0.075 mm, Fg is predominant over Fs. So, thus for the large particle sizes, which includes soil particles in the coarser fraction, that is greater than 0.075 mm, Fg is predominant over surface forces. That is for bulky particles, the ratio Fg is predominant over Fs. Suppose with a decreasing in the particle size, as particle size diameter decreases, the ratio Fg by Fs decreases. That indicates that as the particle diameter decreases, the ratio Fg by S decreases. That means surface forces predominate. So, with an increase in the ratio of Fg by Fs, with an increase in the particle size, the ratio of Fg by Fs increases. With a decrease in the particle size, the ratio of Fg by Fs decreases. So, with an increase in the particle size, gravity forces predominant over surface forces. With a decrease in the particle size, surface forces predominant over gravity forces. That is an important concept we should keep in mind before looking into the particle arrangement of the soil particles. So, let us look soil structure or soil fabric, it is also called as soil fabric. The arrangement of the grains in relation to each other is defined as soil structure or soil fabric. Properties of soil mass, they are basically the function of the arrangement of the grains. The system of the discrete particles or grains that make up soil particles are not strongly bonded together, hence are relatively free to move with respect to each other. So, arrangement of the grains in relation to each other is defined as a soil fabric, and the properties of soil mass is a function of the arrangement of the grains. The system of the discrete particles that make up soil are not strongly bonded together and hence are relatively free to move with respect to each other. According to Tarjagi and Casagrande, the types of the soil structures basically are classified as follows: single grain, honeycomb and flocculent and dispersed structures. This covers both coarse grain and fine grained soils. Size and shape of the grains and minerals from which the grains are formed determine the formulation of a particular soil structure. So, size and shape of the grains and minerals from which the grains are formed determine the formulation of a particular soil structure. So, as per Tarjagi and Casagrande, the types of soil structures are single grained, honeycomb, flocculent and dispersed structure. Single grained and honeycomb are basically for coarse grained particles. Flocculent and dispersed structures are for fine grained soils. If you look into this slide, single grain structure is shown. The structural arrangement of the bulky particles can be seen here. The structural arrangement of bulky particles can be seen in this slide. The particles of different sizes and different shapes can be seen in contact with each other, and the spaces in between these particles can be voids or can be filled with particles of small size. The particle size greater than 0.02 mm, that is for sands and silts, this type of single grain structure can govern. So, in the single grain structure, as we have seen, each grain touches several of its neighbors in such a way that the aggregate is stable even if there are no forces of adhesion, that is no forces of adhesion in the sense no bond or no cohesion at points of contact between the grains. So, each grain touches several of its neighbors in such a way that the aggregate is stable even if there are no forces of adhesion at the points of contact with between the grains. The arrangement may be dense or loose, and the properties of aggregate are greatly influenced by the denseness or looseness. So, the particles can be in a dense packing fashion or a loose packing fashion, and the properties of the aggregate are greatly influenced by the denseness or looseness. For example, if you see a loose state can yield high void ratio and low unit weight. Particle packing with a loose state can yield high void ratio and low unit weight. For example, a particle packing in dense state can yield low void ratio and high unit weight. For granular soils, and that is predominantly for sand and gravel, the range of void ratios are generally encountered can be visualized by considering an ideal situation in which the particles are spheres of equal size. Though the particles are having different shapes, because of their different patterns of arrangements, they are idealized as spheres of equal size. The loosest and densest possible arrangements that we can obtain from these spheres are simple cubic and the pyramidal type of packing respectively. Simple cubic, that is for loose state, and pyramidal type of packing is for dense state. Consider example billiard balls with particular arrangement like this. Different spheres of equal diameter d stacked in a loose fashion, and these are idealized spheres representing soil particles. This is in cross section, and these are the void spaces. So, you can see here with this arrangement large amount of voids can yield maximum void ratio and low unit weight. The other arrangement, which is said as pyramidal arrangement, looks like this. In cross section is shown. You can see the reduction in this is for pyramidal arrangement. For dense packing, this is in the cross section, and voids. It can be seen this reduction in the voids yields minimum void ratio and high unit weight. So, we have seen one is pyramidal simple cubic arrangement for representing the loose state, and pyramidal arrangement for representing the dense packing state. So, let us look into this further. So, that is what it is shown here. A single grain structure in the loose state for both for plan and cross section is shown here, and for dense state of single grained structure in plan is shown here, and these are the spheres at the bottom, and the next level these are the spheres, and these are the spheres in the this sphere will be there at the topmost this thing. So, this arrangement represents the dense packing state, and this arrangement represents the loose packing state. So, in the case of natural granular soils, particles are neither of equal size nor perfect spheres. In the case of natural granular soils, the particles are neither of equal size nor perfect spheres, but we are idealizing like equal spheres. How far they are correct? This can be seen with this following justification. The small size particles may occupy void spaces between the larger ones, and which will tend to reduce the void ratio of natural soils as compared to that for equal spheres. The small size particles may occupy void spaces between the larger ones, which will tend to reduce the void ratio of natural soils as compared to that for equal spheres. Let us look into it, this aspect. Here it can be seen here, between the large particles, large soil particles, the small particles of different soils gets filled and forms densest possible packing. So, this is one extent where the small particles gets packed in between the large soil particles. This can yield densest possible packing, which may be possible, and which can yield minimum void ratio in the natural state. On the other hand, the irregularity in the shape of the particles generally tends to increase void ratio of the soil as compared to ideal spheres. We also discussed, while discussing the shape of the soil grain, we said that the soil can have soil particle can have different grain shapes, and the irregularity in the shape of the particles generally tends to increase void ratio of the soil as compared to ideal spheres. So, this can be looked like this. If you see here in this slide with the figure B here, these are the large void spaces which are formed because of the irregular particle sizes and particle shapes can yield large void spaces. So, the void ratios encountered in real soil are approximately in the same range as those obtained in the case of equal spheres. So, one case represents the densest possible state, the other one represents the loosest possible state. So, let us look further into deductions from this maximum and minimum void ratios. We said that densest possible state of packing of soil grains can yield minimum void ratio, loosest possible state of packing of soil grains can yield maximum void ratio of soil. So, if you see here this first phase diagram, that generally this is a two phase diagram is represented here for the dry sand. Let us consider for a dry sand. In the loosest condition, the void ratio is equal to E max here. So, here the volume of solids and volume of voids, large amount of volume of voids can be noted here. In the densest possible packing, like whatever we have discussed in the previous slide, with that the densest condition represents void ratio E minimum, that is minimum void ratio in densest state. Reduction in the volume of voids can be noted, and the constant amount of volume of solids can be seen here. So, the decrease in volume of voids represents the range over which a particular soil can vary, can have maximum and minimum void ratios. For example, an intermediate condition to which the soil has been found in natural state or compacted while placing can have an intermediate void ratio that will be in between maximum void ratio and minimum void ratio. And here you can see intermediate condition, the void ratio is represented as E or E naught. So, E is the void ratio which is called in situ void ratio or void ratio in the intermediate state, or E max is the maximum void ratio in loosest state, and E minimum is the minimum void ratio in densest state. With this, an important parameter can be defined, that is a parameter called relative density. Before defining relative density, we can also see what is the possible maximum void ratio for the cubic arrangement. If you consider 4 particles of soil idealized as spheres of diameter d, d is the particle size diameter, and if you assume that the maximum void ratio from the cubic arrangement E max is equal to 8d cube, that is nothing but the total volume minus the volume of the solids, that is nothing but equivalent volume of 8 complete spheres, is 4 by 3 pi d cube. 4 by 3 pi d cube is the volume of the solids. So, total volume minus volume of the solids yields to volume of voids towards ratio of volume of solids 4 by 3 pi d cube, that is the volume of 8 spheres in this particular space of cube of size dd, which reduces the maximum possible void ratio is E max is equal to 0.91. So, maximum possible void ratio corresponding to simple cubic arrangement of equal spheres is 0.91. Maximum possible void ratio corresponding to simple cubic arrangement of equal spheres is 0.91. Let us look the formation for minimum void ratio. For pyramidal arrangement, it results in face centered cubic packing. Each sphere lies within the space formed by 4 adjacent spheres in the layer below, and the same pattern is replicated at the bottom and 4 vertical sides of the cube. So, you consider here 4 spheres, and the space in between these 4 spheres is filled by a sphere on the top. If you look here with 4 spheres, the 4 sphere at the bottom, that these are the parts of the 4 spheres, and this yellow one is the sphere at the top, and if you represent this as root 2 d, which is equivalent to 1.414 d, in that if you assume that is as the total volume minus the spheres which are falling within this space represents the volume of solids, that will be 6 spheres and 8 octants or 4 complete spheres. So, by taking 4 complete spheres volume as the volume of the solids, by taking now volume of voids, this is nothing but the volume of voids to the volume of solids, yields the minimum possible void ratio for the pyramidal arrangement in the case of a densest packing. So, for the cubic arrangement, for the loosest state, we said that the maximum void ratio will be around 0.91, and for pyramidal arrangement with in the densest state, the minimum void ratio will be around 0.35. So, having seen maximum and minimum void ratios, now let us define a parameter relative density, which is indicated as d suffix r, which is widely used for indicating the compactness of the soils in case of a coarse grained soils. So, relative density is a term generally used to describe the degree of compaction, packing or togetherness or compactness of the coarse grained soils, and which is defined based on maximum void ratio, intermediate void ratio or in situ void ratio and minimum void ratio, which is given like this here. dr is equal to E max minus E divided by E max minus E minimum. So, this is range between maximum void ratio and minimum void ratio, which may be possible for a particular type of coarse grained soil, and E max is the maximum void ratio and E is in situ void ratio. With this, we will be able to obtain the degree of compaction of a particular soil. So, if you look at this scale here, at E is equal to infinity, the unit weight of the soil is 0, and at the E is equal to E minimum, the soil can have gamma d max, that is maximum dry unit weight. At E max, the soil can have gamma d minimum, that is minimum possible dry unit weight of a soil, minimum possible dry unit weight. So, the range which is indicated between E max and minimum is relative density, which has got a range from 0 to 100, which is generally indicated in percentage. dr is equal to E max minus E by E max minus E minimum into 100. This can also be represented with this equation, gamma d max by gamma d into gamma d minus gamma d minimum, gamma d max minus gamma d minimum. So, if you know the maximum void ratio and minimum void ratio of a given soil which is being used for filling or compacting in a particular area, and by knowing the in situ void ratio, we will be able to determine the compactness or the degree of compaction at particular time. So, which can be indicated with in percentage, and dr is equal to E max minus E by E max minus E minimum into 100, and r which can be also be indicated in terms of unit weights as gamma d max by gamma d into gamma d minus gamma d minus gamma d minimum by gamma d max minus gamma d minimum into 100. This gives the possible degree of compaction of coarse grained soils. Relative density for coarse grained soils, particularly granular soils, can be indicated with this following classification. dr, that is relative density, if it is less than 15, is the state is reported to be very loose. If the relative density is in the range from 15 to 35, indicated as a loose state, 35 to 65 medium dense, 65 to 85 dense state, and greater than 85 is very dense state. So, the soil greater than soil with a relative density greater than 85% indicates a very dense packing. Soil with relative density less than 15% indicate very loose packing. The relative density of sand has a well defined meaning because of its value is practically independent of static pressure to which the sand is subjected. It depends primarily nature and denseness of the arrangement. So, it is possible for two sands, for example, to have void ratios and relative densities significantly different fabrics, thus significantly different engineering behavior. It is possible for two sands, for example, to have identical void ratios and relative densities, but significantly different fabrics, thus significantly different engineering behavior. So, two sands, even if they have identical void ratios and relative densities, but it is possible that their single grain arrangement can be different, can yield to a different engineering behavior. So, the relative density of sand has a well defined meaning because of its value is practically independent of the static pressure to which the sand is subjected. It depends primarily nature and denseness of the arrangement. The next soil structure which is possible is defined as a honeycomb structure. This is for grains of silts smaller than 0.02 mm and larger than 0.002 mm, that is 2 micron. They settle out of suspension more or less as single grains, but are so small that the molecular forces at the contact area are large enough compared to the submerged weights, that is the gravity forces, to prevent the grains from rolling down immediately to the positions of the equilibrium among grains already deposited. So, that indicates here, if you see here, because of the because at the contact points here the molecular forces dominate the submerged weight forces, with that they form miniature arches and create a structure called a honeycomb structure with large void ratios. So, grains coming in contact are held by forming miniature arches. So, these arches bridging over relatively large void spaces. Void spaces like this can exist in the honeycomb structure, and these honeycomb structure, once these arches collapse, they reduce to again a single grain particle arrangement. So, the second type of soil structure arrangement for silt to clay particles, that is particles greater than clay particles, yields to a honeycomb structure where the molecular forces at the contact areas dominate the surface forces, that dominate this submerged weight forces, which cause grains coming in contact are held by forming miniature arches and bridging over relatively large void spaces. So long as these arches are stable, the honeycomb structure is stable. Once this honeycomb structure collapses, it yields to, or it again transforms into a single grain structure. Now, having seen structural arrangement of the particles for silt and sand particles and gravel particles, let us look into the structural arrangement of clay soils, that is basically represent fine grained soils. So, for this we have to look into the particle forces and behavior and their influence in forming the structural arrangement in case of clay soils. The forces between clay mineral particles: if two particles platelet shape approach each other in suspension, the forces acting on them are van der Waals forces of attraction. There will be a certain forces of attraction between the particles. The repulsion between the two positively charged ionized adsorbed water layers. If you see here, the clay particle surface is represented here with the net negative charge, and a rigid layer, that is with systemized arrangement of the ions with within very close to the particle. We said that is as an adsorbed water layer, which imposes with another particle when it comes in contact, the repulsion between two positively charged ionized adsorbed water layer exists. In addition to this, the particles also will have van der Waals forces of attraction. So, these two influence in making the particles settle in the suspensions. So, let us look how these two attraction and repulsion forces influence this particular arrangement. At very small separations, the van der Waals forces are always larger, and particles which approach sufficiently closely will adhere. However, the van der Waals forces decrease rapidly with increasing separation. So, if you look into this diagram, the net force between two parallel particles in suspension is shown, and on this axis distance between crystal faces is shown here. With an increase in the distance between crystal faces, you can see the decreasing attraction force. So, particles very close to that, they have a strong attraction, that is because of the van der Waals forces. That is what it has been told here. At very small separations, the van der Waals forces are always larger, and particles which approach sufficiently closely will adhere. However, the van der Waals forces decrease rapidly with increasing separation. That is here a clay particle with an absorbed layer is shown here, and they are subjected to repulsion. If the absorbed layer is thick, the repulsion will be large at distances from the surface at which the van der Waals forces are small. That means that if you look into here, for a particular distance away from the clay space, clay particle, there will be net force, repulsion can dominate, and very close to the particle there may be a chance that these van der Waals forces of attraction dominate. So, these two determine in the particle arrangement for the fine grained soils. So, if the adsorbed water layer is thick, the repulsion will be large at distances from the surface at which the van der Waals forces are small. So, with this because of this region, the particles will remain in a dispersed state, settle independently. When net force is repulsion, that means that when repulsive forces overcome these van der Waals forces of attraction, then it results in a dispersed state. Particles will remain in dispersed state and they settle independently without being coming in contact with each other. However, the contact between the dispersed particles can be established if an external force is applied which is large enough to overcome the net repulsive forces. Suppose if these dispersed particles can be can be pushed together by applying an external force which should be large enough to overcome the net repulsive force. So, contact between dispersed particles will only be established if an external force is applied and which is large enough to overcome net repulsive force. If the adsorbed layer is thin, previous case if the adsorbed layer is thick and at a certain distance from the clay particle, and if the net force is repulsion, we said that there is a possible state of arrangement that is called a dispersed state, where the particles settle independently. In the other case, if the adsorbed water layer is thin, there will be little or no net repulsion at any distance, and random movements of particles will be enough to bring them into contact, and this process is called flocculation. You can see the particles flock with each other and form a contact like this, in which where the attraction is the net force here, where attractive forces or dominated the repulsive forces, and which make the particles to remain in contact with each other, which forms with this type of pore void spaces in between these particles. So, groups of particles settle together or flock together. So, this particular arrangement is called flocculation or a flocculated structure, which we are going to see now. So, this is what it has been shown here. Net force between two particles in a suspension. In case of a low ion concentration, you can see that there is a predominantly a net repulsion is dominating. In case of a high ion concentration in the say soil water, then net attractive forces dominate here. So, when the particles come in contact, when they settle in a suspension, and if in case of a high ion concentration in the soil water, that can result in flocculated type of arrangement, and if net repulsion is dominating in case of a low ion concentration in the soil water, that can result in a dispersal type of arrangement. So, let us look into these two structures which we defined from their influence of the particle forces and their and behavior. One, we said the dispersed structure. So, the dispersed structure of the clay soils, the net forces of repulsion are greatest in the case of particles approaching face to face. So, the particles can come here as shown here face to face in the soil water because of the low ion concentration and thick adsorbed water layer, the net force will be repulsion. So, this type of deposit is possible for lacustrine clays, that is deposited in freshwater lakes, generally have a dispersed structure. In this case, few of the particles are in direct contact, most being separated by the adsorbed water layers. So, a dispersed structure can be there in lacustrine clays that deposited in the freshwater lakes, generally have a dispersed structure. In this case, few of the particles are in contact and most being separated by the adsorbed water layers. In the case of dispersed structure, the edges, corners and faces of the clay particles have like electrical charges. So, with that, thus the particles repel each other and assume nearly parallel positions. So, parallel arrangement or with the face to face repulsion will be there in the dispersed structure. Even though the dispersed structure may be quite loose at the time of sedimentation, pressure can force the adjacent particles into a dense state. So, even though the dispersed structure may look quite loose at the time of sedimentation, pressure can force, that means with the help of an external force that may be possible with the loading, can force the adjacent particles into a dense state. So, in the case of dispersed structure, the edges, corners and faces of the clay particles have like electrical charges. Because of this, the particles repel each other and remain in nearly parallel positions. Even though the dispersed structure may be quite loose at the time of sedimentation, pressure can force the adjacent particles into a dense state. Flocculate structure of clays, the marine clays, it generally occurs in marine clays deposited in seawater in which ion concentration is high, so that the adsorbed water layer is thin, generally have flocculated structure. So, in which the ion concentration is high, it results in a flocculated structure. So, marine clays in the coastal deposits, coastal sites have flocculent structure. So, flocculent structure can be there in marine clays deposited in sea water in which ion concentration is high. So, that the adsorbed water layers are thin, generally have flocculated structure. Flocculated structures has open structure like this is shown here. You can see here face edge to face interaction or face to edge interaction here can be seen between different particles, and they form a open mesh structure with large void spaces. So, flocculate structure has open structure with large void spaces with particles attached to each other and with edge to edge or edge to face contacts. So, there may be possibility that they can get attached with edge to edge connection or edge to face like this here. Edge of this particle is attached to this face of this particle. So, in the case of flocculate structure, the particles assume a loose but fairly stable structure that can be maintained as long as the electrical charges on the edges of the platelets remain opposite in sign to those on the faces of the particles. So, the degree of looseness of a flocculate arrangement is a function of the nature and amount of electrolytes present during sedimentation. So, in the case of a flocculate structure, the particles assume a loose but fairly stable structure that can be maintained as long as the electrical charges on the edges of the platelets remain opposite in sign to those on faces of the particles. So, here a typical arrangement of the platelet particle is shown. So, where here a typical plate shaped particle is shown as dispersed arrangement in the low ion concentration, where the medium is predominantly acidic medium, which can yield to a dispersed state. For practical significance, this can be there in quite lakes or lacustrine clays, and this arrangement can be there, flocculated arrangement can be there for marine clays with high ion concentration, where you can see edge to face attachment can yield a open mesh flocculated arrangement. So, here in this a structure of undisturbed flocculent structure of the marine clay is shown here, and this particle represents the silt size particle with oval shape, and they also get formed and attached to these particles with the clay particles with platelet shape. The clay particles are represented by a platelet shapes here, which is shown here. So, a clay with an undisturbed flocculate structure will possess large void openings. So, the flocculated structure, the soil formed with flocculated structure have larger void openings. When platelet particles are carried into freshwater lake, they do not flocculate and settle along the silt particles as they do in the salt water. So, here a remolded or dispersed structure of the freshwater deposit can be seen with the parallel arrangement of the clay particles in between the silt particles are shown here. So, remolding of flocculated structure results in dispersed structure. So, if you remold any soil with flocculated structure, that results into a dispersed structure. So, here this also represents remolded or the dispersed structure of freshwater deposits. So, having seen different particle arrangements, we said that for single grained arrangement can be there for bulky particles. Honeycomb structure can be possible for silt particles predominantly, and for coming to the clays representing fine grained soils can have flocculent structure as or dispersed structure. It depends upon the environment in which the suspension is occurring. Then the question will come, how to identify the soil structure. One of the methods for coarse grained soils is to use ordinary microscope, which is valid for coarse grained soils only. For looking for particle arrangement in case of a clay soils, scanning electron microscopy SEM method is widely used. In this scanning electron microscopy, it uses electrons rather than the light to form an image, and involves the preparation of the thin section and allows us to look the 2D arrangement of the particulate arrangement only. So, this is ideally suited for clay soils as the resolution is sufficiently high, and hence it is possible to go for higher magnification. One can go up to 10 to the power of 5 types of magnification. So, scanning electron microscopy, which is used for obtaining the 2D arrangement of the clay soils. Let us discuss the procedure about scanning electron microscopy. It involves sample preparation. First is that removal of the pore water without changing the particular arrangement. Generally, carbowax is used. The preparation of the cubic shape of size 1 centimeter cube and fractured. Then application of electrically conductive coat on fractured surface by using a special technique. Generally, in this thin gold coating is applied with the sputter coater, and focusing of an electron beam to a fine point and is scanned over the surface, and a collection and amplification of the secondary electrons in the electron gun, and the output is fed from the electron gun to the display unit. The image formed has a magnification and is photographed. So, the procedure for obtaining the particulate arrangement through scanning electron microscopy involves removal of the pore water without changing the particulate arrangement. Generally, the carbowax is used, which melts at 55 degrees centigrade, and the preparation of the cubic shape of size approximately 1 centimeter cube, and it is required to be fractured, and application of the electrically conductive coat on the fractured surface by using a special technique. Generally, thin gold coating is given, and focusing of an electron beam to a fine point and is scanned over the surface. After that, the collection and amplification of the secondary electrons in the electron gun, the output is fed to the display unit, which gives the image has a magnification, and it is photographed to know about the particular arrangement of clay soils with the help of the scanning electron microscopy method. So, in this lecture, we have seen about the particulate arrangement in coarse grained soils and fine grained soils, and we said that different types can be possible as per the classification of the Terzaghi and Casagrande, single grained, honeycomb, and flocculated or dispersed. And we also discussed about the loose and dense sand deposits, which is possible. An important parameter, relative density for coarse grained soils have been defined, and we also deduced the reasons for different arrangements for dispersed and flocculent structures, and the forces between the clay minerals with van der Waals forces of attraction and repulsion forces which can between two adsorbed water layers, which may determine the forces between the clay particles have been discussed, and which yield to dispersed and flocculent structures.